Question 5 of this exercise says D, E and F are respectively the midpoints of sides AB, BC and CA of triangle ABC. So let's draw a figure corresponding to this statement. So here's an arbitrary triangle ABC that I've drawn, and we are told that D is the midpoint of AB. So D would be here. E is the midpoint of BC, so E would be somewhere here, and F is the midpoint of CA, so F would be, let's say, here. And now we have to find the ratio of the areas of triangle DEF and triangle ABC. So let's complete triangle DEF by joining DE and F. So we have DE, we have then EF, and we have DF. So we have to find the ratio of areas of the small triangle DEF and triangle ABC. So let me first describe the logic that we will use to solve this problem. So we will use the midpoint theorem, and we will show that this small triangle DEF, it's similar to the big triangle ABC. How? Well, if we look at the sides of DEF, we can see that DE, using the midpoint theorem, DE will be half of the side CA of triangle ABC. Similarly, EF will be half of AB, and FD will be half of BC. So if you look at the ratio of corresponding sides of triangle, the small triangle DEF and the big triangle ABC, the ratio of corresponding sides will be the same. And we can apply the SSS similarity and say that the two triangles are similar, and from there we can find the ratio of the areas easily, because for any two similar triangles the ratio of areas is square of ratio of corresponding sides. Okay, so this is what we are going to do to solve this problem. So as I said, using the midpoint theorem, we can say that DE, this segment joins the midpoints of AB and BC, so it will be equal to half of the third side. So DE will be equal to half of CA, and EF will be equal to half of AB. So as I'm writing this, observe the relevant segments in the figure carefully. And similarly, FD will be equal to half of BC. And the reason for all of these equalities is the midpoint theorem. The midpoint theorem says that if you join the midpoints of any two sides of a triangle, the segment you get will be parallel to the third side and equal to half of the third side. Okay, now let's say that these equalities, all of these form the set of equalities 1. So from this set of equalities, so from 1, we can now calculate the ratio of corresponding sides. So we can say that DE by CA, so DE by CA will be equal to half, EF by AB will be equal to half, and FD by BC will be also equal to half. So DE by CA equal to EF by AB equal to FD by BC. All three ratios are equal to half, and therefore the two triangles will be similar. But what is the ratio of corresponding sides? So if we take the large triangle as ABC, then corresponding to vertex A, we will have vertex E. Make sure that you understand this fact. Why corresponding to A, it will be E. And corresponding to vertex B, we will have vertex F. And corresponding to vertex C, we will have vertex D. This is the only way you will get these three ratios to be equal, if this is the correspondence of the vertices. Okay, so the way we will write the similarity relation is triangle, if we take the large triangle as triangle ABC, then we will have to write the vertices of the small triangle as EFD. So triangle EFD is similar to triangle ABC, and we are using the SSS similarity criterion to claim this similarity. Now let's make use of the fact that for any two similar triangles, the ratio of areas is equal to square of ratio of corresponding sides. and therefore the ratio of areas, so ratio of area of EFD by area of ABC, so this ratio will be equal to, let's take the ratio of any pair of corresponding sides. So let's take DE by CA, the first ratio. So this will be equal to DE by CA and the square of this, and DE by CA is simply equal to half, so we get half square, or we get 1 by 4. So the ratio of areas is simply equal to 1 by 4. So let's write this. The ratio we get is 1 by 4, or we can write this as 1:4. So this is the answer. The ratio is 1:4, which basically means that the area of the small triangle DEF is 1/4 the area of the large triangle ABC. Now let me show you a slightly different way to solve this same problem. So once again, let's start with triangle ABC. Let's take the midpoints DEF. So D is the midpoint of AB, E is the midpoint of BC, and F is the midpoint of CA. And let's join the three midpoints to get this triangle DEF. Okay, and now we have to find the ratio of areas of DEF and ABC. So in this second approach, what we will do is we will compare the triangle ADF, which is this triangle, to the big triangle ABC. So let me highlight the big triangle also, ABC, this whole triangle, and we will show that these two triangles are similar. Okay, and from this similarity we will find that the ratio of triangle the area of triangle ADF is 1/4 the area of triangle ABC. Similarly, we can then say that the area of triangle BED is also 1/4 the area of ABC, and the area of triangle CFE is also 1/4 the area of ABC. So these three triangles put together will form 3/4 the area of ABC, which will leave you with this triangle DEF, which will then be 1/4 of the area of triangle ABC. So this is what the logic that we will use in this second approach. So let me write it now. So we are basically comparing ADF and ABC, the triangle ADF and ABC, and to show that they are similar, we make use of the midpoint theorem once again. So we say that DF is parallel to BC, and also DF is equal to half of BC, correct? Because this is basically the midpoint theorem. Okay, and now if we compare the triangles ADF and ABC, so in triangle ADF and triangle ABC, how can we show that these two triangles are similar? Well, this angle at A is common to both the triangles, and then this angle at D in triangle ADF will be equal to this angle at B in triangle ABC, because these are corresponding angles, because DF is parallel to BC. Okay, so let's write this. Angle A is equal to angle A, basically because this is a common angle, and angle ADF is equal to angle ABC, because these are corresponding angles, and therefore the triangle ADF is similar to triangle ABC, and this is basically the AA similarity criterion. Alright, now let's make use of the fact that for two similar triangles, the ratio of areas will be the square of the ratio of corresponding sides. So now we can write the area of ADF by the area of ABC. This ratio will be equal, because these two triangles are similar, this ratio will be equal to, let's take the ratio of any pair of corresponding sides. So let's take DF in the first triangle and BC in the second triangle. So DF by BC whole square. But DF by BC is simply half, because DF is half of BC. So DF by BC is half, so we get half square, or we get 1 by 4, correct? So from here we can say that area of ADF is equal to 1/4 the area of triangle ABC. And now similarly, as I said earlier, similarly we can say that the area of triangle BED, let me highlight this triangle also, BED would be this triangle. Let me use a different color, BED. This would also be 1/4 of ABC, and then CFE would be CFE, this triangle. This would be also 1/4 of ABC. So let's write this these arguments. So similarly, the area of triangle BED and the area of triangle CFE, these two areas will also be equal to 1/4 the area of triangle ABC. Okay, so this means that the area of the triangle ADF, BED and CFE, these three areas put together will be 3/4 the area of triangle ABC. So that leaves us with only this area, the area of triangle DEF, and therefore we can say that the area of triangle DEF is the area of triangle ABC, so the whole area, minus 3/4 the area of ABC. So this will be 1/4 the area of ABC. So once again we find that DEF is 1/4 of ABC, or the required ratio is 1:4, which is what we obtained in the first approach also. So in the first approach we basically directly showed that triangle DEF is similar to triangle ABC using the SSS similarity, and from there we found the ratio of areas. In the second approach we took a slightly longer path. We calculated the area of ADF, of BED and CFE in terms of the area of triangle ABC, and we subtracted all these three areas from the area of triangle ABC to find the area of DEF. So you can use both approaches. Both approaches are correct, but if you ask me personally, I prefer the first approach because it's much shorter and you can directly show that the smaller triangle is similar to the larger triangle using the SSS similarity. Okay, so this completes question number 5.
To learn more about how QMath can help you crack school and board exams, explore QMath Leap, a live online classroom program run by highly experienced and committed teachers.